Hello everyone, I am B. Chiranjeev Rao, Assistant Professor, Electrical Engineering Department at Sri Shankaracharya Technical Campus, Bhilai. Welcome you all to lecture number 4 of week 10. In last lecture, that is lecture number 3, we started our discussion with the speed control of DC motor using DC drive. Today, we will begin our lecture by discussing speed control of DC motor using 3-phase DC drive and chopper drives. So, first we start with 3-phase full wave converter. The 3-phase full wave converter is a fully controlled bridge control rectifier using 6 thyristor connected in the form of full wave bridge configuration. All the 6 thyristor are controlled switches which are turned on at a suitable times by applying proper gate trigger signals. The 3-phase full converter is extensively used in industrial power application where 2-quadrant operation is required. The 3-phase fully controlled rectifier control fed separately excited DC motor drive is shown in the figure. Thyristor are fired in the sequence of their number with a phase difference of 60 degree by gate pulses of 120 degree duration. Each thyristor conducts for 120 degree and 2 thyristor conduct at a time, one from upper group and the other from lower group, applying respective line voltage to the motor. Transfer of the current from an outgoing to incoming thyristor can take place when the respective line voltage is of such a polarity that not only it forward biases the incoming thyristor, but also lead to the reverse biasing of the outgoing when incoming turns on. Thus, firing angle of a thyristor is measured from the instant where the respective line voltage is 0 and increasing. For example, the transfer of current from thyristor T5 to thyristor T1 can occur as long as the line voltage VAC is positive. Hence, for thyristor T1, firing angle alpha is measured from the instant when VAC is equal to 0. The motor terminal voltage and current waveform for continuous conduction are shown in the figure for motoring and braking operations respectively. Device under conduction are also shown in the figure. The discontinuous conduction is neglected here because it occurs in a narrow region for its operation. For the motor terminal voltage cycle from alpha plus pi by 3 to alpha plus 2 pi by 3, VA is equal to 3 Vm upon pi into cos alpha. It offers 2-quadrant drive and it use up to about 1500 kilowatt drives. This drive operates in quadrant 1 and quadrant 4. The circuit diagram consists of one 3-phase full converter in armature circuit and another 3-phase full wave converter in field circuit is shown in the figure. For regenerative purposes, the polarity of counter EMF is reversed by reversing the field excitation by making the firing angle delay of converter 2 more than 90 degree. For converter 1 in armature circuit, the average output voltage is given by V naught is equal to 3 Vm upon pi cos alpha 1, where alpha lies between 0 to pi, and for converter 2 in field circuit, Vf is equal to 3 Vm upon pi cos alpha 2, where alpha 2 lies between 0 to pi, where Vm is the maximum value of the line voltage. So, both the armature voltage and field voltage depends on their respective firing angle. So, we can vary armature terminal voltage and field voltage by varying the respective firing angles. Now, next topic is dual converter fed DC motor drive. In many variable speed drives, the 4-quadrant operation is generally required and 3-phase dual converter are extensively used in application up to 2 megawatt level. A dual converter is defined as an electronic circuit with 2 converter, one as a rectifier and the other as an inverter. A dual converter control of DC separately excited motor is shown in the figure, which consists of 2 fully controlled rectifiers connected in anti-parallel and connected to the same DC load, allowing for 4-quadrant operations. For power rating up to 100 kilowatt, single phase fully controlled rectifier can be used. For higher rating, 3-phase fully controlled rectifiers are employed. Rectifier A, which provides positive motor current and voltage in either direction, allows motor control in quadrant 1 and quadrant 4. Rectifier B provides motor control in quadrant 2 and 3, because it gives negative motor current and voltage in either direction. For reversing the polarity of the motor generated EMF for generation purpose, field current must be energized from single phase or 3-phase full converter. When converter 1 or converter 2 is in operation, average output voltage is V naught is equal to 3 V m upon pi cos alpha, for alpha lies between 0 to pi. There are 2 different mode of operation of 3-phase dual converter system: simultaneous control or circulating current mode of operation. Another one is non-simultaneous or circulating current free or non-circulating mode of operation. In simultaneous control, both the rectifiers are controlled together in the order to avoid DC circulating current between rectifiers. They are operated to produce same DC voltage across the motor terminals. Although control of the firing angle according to the relation, the sum of both the firing angles of rectifier A and B must be equal to 180 degrees. Prevents DC circulating current, AC prevents DC circulating currents. AC current does circulate due to difference between instantaneous output voltages of 2 rectifiers. Inductor L1 and L2 are used only with simultaneous control. Inductor L1 and L2 are added to reduce AC circulating current. Because of the flow of AC circulating current, simultaneous control is also known as circulating current control. In a 3-phase dual converter, inductor are chosen to allow a circulating current of 30% of full load current. This completely eliminates discontinued conduction and therefore gives full speed regulation in the complete range of the drive. The second method is non-simultaneous or non-circulating current control method. In this method, one rectifier is controlled at a time. So, as a result, no circulating current flows and inductor L1 and L2 are not required in this case. This eliminates losses associated with circulating current and the weight and volume associated with inductor. But then discontinuous conduction occurs at light loads and control is rather complex. Now, next topic is single phase DC series motor drive. In the single phase DC series motor drive, the field is connected in series with the armature. The field current is the same as the armature current. Single phase DC series motor drive fed from a phase control converter is shown in the figure. DC series motor are capable of high starting torque and constant power operation at all speeds. They generally use in traction, cranes, hoists, etc. In a separately excited motor, there is always a back EMF present which actually accelerates the decay of armature current, thereby making discontinuous conduction occur, particularly at low currents. Discontinuous conduction over a wide range of operating condition. On the other hand, in series motor, the back EMF being proportional to does not, as the motor current decreases, it tends to become continuous, unlike in the case of separately excited motor. A single phase half control rectifier control of DC series motor is shown in the figure. The equivalent circuit of the motor is also shown. Since back EMF decreases with armature current, discontinuous conduction occur only in narrow range of operation. Hence, it can be neglected. Although in steady state fluctuation in speed are negligible, the back EMF E is not constant, but fluctuate with armature current I A. For a given speed, back EMF is related to I A through magnetization curve of the motor, which is non-linear owing to saturation. A cycle of motor terminal voltage consists of 3 intervals. Due to intervals, when omega t is between alpha and pi, that is when motor is connected to the source and armature voltage is equal to supply voltage V s. The freewheeling interval when armature current is 0 and omega t lies between pi to pi plus alpha. Next, we deal with the control of fractional HP motor. Because of low cost single phase half wave control rectifier shown in the figure, employing a single thyristor is commonly used for the control of fractional HP universal DC series and permanent magnet DC motor. Such drives are employed in hand tools and small domestic appliances. Motor terminal voltage and armature current waveform for universal motor are shown in the figure. The drive operates in discontinuous conduction with a large zero current interval and large current ripple. As a result, efficiency is poor, speed regulation is large and speed may fluctuate around its average value where the inertia is low. Sometimes a freewheeling diode is added to reduce the duration of zero current interval. A series motor has torque speed characteristics, making it suitable for constant power operation. However, when it fed from a converter, it does not exhibit constant power operation at all speed for a given firing angle. To achieve constant power at all speed, adjustment of firing angle is made. Universal motor may also be controlled by a track AC voltage controller shown in the figure. The track is fired at alpha and pi plus alpha. Now, the machine armature carries AC current as shown in the figure. Because of reduced duration of zero current interval, the drive has negligible speed fluctuation and low speed regulation. So, next topic is chopper drive. The chopper converts the fixed DC voltage to variable DC voltage. Self-commutated device like chopper, self-commutated device like MOSFET, IGBT, power transistor, GTO are used for making chopper because they can be commutated by low power control signal and do not need commutation circuit. When variable DC voltage is to be obtained from fixed DC voltage, a DC chopper is ideal choice. Use of chopper in traction system is now accepted all over the world. This results in overall energy saving, which is the most welcome feature in the transportation system requiring frequent stops. As for example, in rapid transit system, a chopper is inserted in between a fixed voltage DC source and the DC motor armature for its speed control below base speed. In addition, chopper is easily adaptable for regenerative braking of DC motor, and thus kinetic energy of the drive can be returned back to the DC source. The chopper operated at high frequency, due to which it upgrades the motor performance by decreasing the ripple and removing the discontinuous conduction. The most important feature of chopper control is that the regenerative braking is carried out at very low generating speed. When the drive is fed from a fixed voltage at low DC voltage, the variable voltage to the armature of a DC motor for speed control can be obtained from a DC chopper, which is a single stage DC to DC conversion device. Chopper drives are also used in battery operated vehicles, where energy saving is prime importance. There are several advantages like high efficiency, controlling flexibility, lightweights, small size and fast response of the chopper drive. There are two different modes of operation of a chopper drive system. First one is power control or motoring control, and second one is regenerative braking control. So, first start with power control or motoring control. The figure shows basic arrangement of DC chopper feeding power to a separately excited DC motor. The chopper shown to be consist of a force commutated thyristor. This drive generally offers one quadrant drive operation. A transistor chopper control of separately excited DC motor as shown in the figure consists of transistor TR is operated periodically with period T and remains on for a time duration T on. Present day chopper operates at the frequency which is high enough to ensure continuous conduction. Waveform of motor terminal voltage VA and armature current IA for continuous conduction are shown in the figure. During on period of the transistor, that is when time is between 0 to T on, the motor terminal voltage is capital V. In this interval, armature current increases from IA1 to IA2. Since motor is connected to the source during this interval, it is called duty interval. At t is equal to T on, TR is turned off. Motor current freewheels through diode DF and motor terminal voltage is 0 during this interval when t is between T on and capital T. Motor operation during this interval is known as freewheeling interval. The average motor voltage V naught is equal to T on by T into V s or is equal to del into V s, where del is known as duty ratio and del is equal to T on by capital T. Now, next is regenerative braking. In regenerative braking, the motor acts as a generator and the kinetic energy of the motor and connected load is returned to the supply. During motoring mode, armature current IA is equal to Vt minus Ia by Ra, where Vt is terminal voltage, Ea is back EMF and Ra is the armature resistance. That is, armature current is positive and the motor consumes power. In case load drives the motor at a speed such that average value of the motor counter EMF E exceeds Va, then Ia is reversed and the power is delivered to the DC bus. The motor is then working as a generator in regenerative braking mode. The chopper control of separately excited DC motor for regenerative braking operation is shown in the figure. Transistor TR is operated periodically with a period T and on period of T on. Waveform of motor terminal VA and armature current IA for continuous conduction are shown in the figure. Usually an external inductance is added to increase the value of LA. When TR is on, IA increases from IA1 to IA2. The mechanical energy converted into electrical by motor now working as generator partly increases the stored magnetic energy in armature circuit inductance and remainder is dissipated in armature resistance and transistor. When TR is turned off, armature current flows through diode D and source V and reduces from IA to IA1. The stored electromagnetic energy and energy supplied by machine is fed to the source. The interval T lies between 0 to T on is called energy storage interval and time interval where T lies between T on to capital T is duty interval. Regenerative braking of chopper fed separately excited DC motor is stable. DC series motor however offers unstable operation characteristics during regenerative braking. As such, regenerative braking of chopper control series motor is difficult. Now, next topic is two quadrant chopper drive. A two quadrant converter is used where regeneration is required. Due to unidirectional current carrying property of thyristors, the two quadrant operation is achieved by changing the polarity of voltage, retaining the direction of the current. However, for reversing the direction of the rotation and achieving the speed control in reverse direction, one should be able to reverse the direction of armature current with voltage variation from a positive maximum to negative maximum. Motoring control circuit for chopper drives offer only first quadrant drive, because armature voltage and armature current remain positive over the entire range of speed control. In regenerative braking, second quadrant drive is obtained as armature terminal voltage remain positive, but direction of the armature current is reversed. In two quadrant DC motor drive, both motoring mode as well as regenerative braking mode are carried out by one chopper configuration. One such circuit is shown in the figure, which consists of two chopper CH1 and CS2 and two diodes D1 and D2 and a separately excited DC motor. First mode is motoring mode. When chopper CH1 is on, the supply voltage V gets connected to armature terminals and therefore, armature current I raises. When CH1 is turned off, I free wheels through D1 and therefore, current I decays. This shows that with CH1 and D1, motor control in first quadrant is obtained. Next mode is regenerative mode. When CS2 is turned on, the motor act as a generator and the armature current I rises and therefore, energy is stored in armature inductance L. When CS2 is turned off, D2 gets turned on and therefore, direction of I is reversed. Now, the energy stored in L is returned to DC source and second quadrant operation is obtained. In the figure, first quadrant operation of DC motor is called forward motoring mode and second quadrant operation is known as forward regenerative braking mode. Now, the last topic is 4 quadrant chopper drive. In 4 quadrant DC chopper drives, a motor can made be work in forward motoring mode, that is first quadrant. Next is forward regenerative braking mode, that is second quadrant, reverse motoring mode, that is third quadrant, and reverse regenerative braking mode, that is fourth quadrant. The power can flow either from source to load or load to source in this chopper. So, next we will see working principle of this 4 quadrant chopper. The circuit of a 4 quadrant chopper basically consists of 4 semiconductor switches CH1 to CH4 and 4 diodes D1 to D4. The 4 diodes are connected in anti-parallel. The circuit diagram of this type of chopper configuration is shown in the figure. This circuit consists of 4 chopper, 4 diodes and a separately excited DC motor. So, first mode is forward motoring mode. During this mode, chopper CS2, CS3 are kept off, CH4 is kept on where CH1 is operated. When CH1 and CH4 are on, motor voltage is positive and positive armature current rises. When CH1 is turned off, positive armature current free wheels and decrease as it flow through CH4 and D2. In forward regenerative braking mode, CH1, CH3 and CH4 are kept off whereas CS2 is operated. When CS2 is turned on, negative armature current rises through CS2, D4, E, L and resistance R. CS2 is turned off when diode D1, D2 are turned on and the motor acting as generator return energy to the DC source. Reverse motoring mode. In reverse motoring mode, chopper CH1, CH4 are kept off, CH2 is kept on where CS3 is operated. When CS3 and CS2 are on, armature get connected to source voltage V, so that both armature voltage V and armature current IA are negative. As armature current is reversed, motor torque is reversed and as a result motoring mode in third quadrant is obtained. The last mode is reverse regenerative braking mode. In this mode, CH1, CH2 and CH3 are kept off whereas CH4 is operated. When CH4 is turned on, positive armature current IA rises through CH4, D2, RA from CH4, D2, R, L and E, where CH4 is turned off, diode D2, D3 being to conduct and motor acting as generator return energy to the DC source. So, we stop here for today's lecture. Thank you for kind attention and participation in the today's lecture. Have a great day. Thank you everyone.